Good luck to everyone. I look forward to your session.
Thank you. Hello, good afternoon, good morning, good evening, depending on where you are. Welcome to session number 4 of our workshop on knowledge-guided machine learning, which deals with weather and climate. Libby and I, who are moderating the session, will introduce ourselves in a second, but we just wanted to point out again, over here on the right of the slide, there's a Slido link. Please use it. We really welcome questions from the audience. So if you have any questions, just type them in there. If you want to do it anonymously, you can do that too, or you can do that with your name. So with that, next slide, please. So my name is Imme Ebert-Uphoff, and I'm a research professor in the Department of Electrical and Computer Engineering. And I'm also the machine learning lead for the Cooperative Institute for Research in the Atmosphere, both at Colorado State University. And maybe more importantly, I've been in the area of data science and climate and weather for about 10 years.
And my name is Elizabeth Barnes, and I'm an associate professor in atmospheric science at Colorado State University. And while my training is really on the atmospheric science side, the past few years I've done quite a bit of work with my group on thinking about data science tools, including machine learning and knowledge-guided machine learning, to do climate and weather science. And Imme and I are close collaborators and lucky enough to introduce this session on knowledge-guided machine learning for weather and climate.
So before we jump into this topic of knowledge-guided machine learning for weather and climate, we wanted to talk a little bit about what exactly we mean by what is included in knowledge-guided machine learning. So as you see on the top left over here, we define knowledge-guided machine learning to be any method that connects scientific knowledge and machine learning. And this includes specifically methods that add scientific knowledge to machine learning algorithms, but also methods that extract scientific knowledge using machine learning, and any combination of the above. Next slide. What is not KGML? Well, there are already hundreds of examples of successful use of machine learning in weather and climate, but most of them are purely data-driven. So pure machine learning, as already used for some of the applications listed here, are not KGML if the approach is purely data-driven and not using or extracting scientific knowledge. So then it's not KGML. Next slide. Just especially for those of you who might not be in the area of weather and climate, we just wanted to give you a little bit of background as to what's special about weather and climate. And on this side, we have data. On the next slide, we have specific machine learning challenges. So some sample data sources in weather and climate are observations from the ground, space-borne observations, complex climate models, and simplified numerical models. And also to give you an idea of the data amounts, they range from very few to very large volume. So a climate model output can deliver 20 petabytes of data. But if you're studying smoke profiles, you might only have 10 fires per year. Next slide, please. So again, what are some of the challenges of using machine learning for weather and climate? So on the left-hand side, you see lots of challenges that are just based on the process and the data. So the Earth is a very complex system, so you have complex interactions in the Earth system at many different scales. Data is often multi-scale and multi-source. Processes are spatial temporal, and you have objects with fuzzy boundaries. So for example, if you have a classic image processing problem of finding cats and dogs, it's very easy to figure out where the cat ends and the dog starts. If you have a heat wave, it's much harder to figure out where exactly does the heat wave end. If you look on the very right side, what's in blue over here, we wanted to point out that many decisions in weather and climate are really live-death decisions. So you may have to make decisions on the spot whether you should evacuate people in one area or another. Furthermore, machine learning methods are fairly new in most climate and weather applications, and most atmospheric scientists are not trained in statistics or computer science. So it's really not surprising that meteorologists do not like to use tools they do not understand, because at the end of the day, they're responsible for those live-death decision-making. So we have all these challenges, but as you see here at the bottom, we also have something that can help us a lot. Namely, atmospheric scientists have collected centuries of knowledge. And so we can put that to good use to try to address some of the challenges over here. Next slide, please. So how can knowledge-guided machine learning help? If you add knowledge to machine learning, it can help in a variety of ways. It aligns methods more with what atmospheric scientists are already using. And if you remember that they're not used to statistics and machine learning, that's really helpful. It can also compensate for small sample size, which we often encounter. Remember, only 10 fires in one summer. It can help for faster convergence of your machine learning model. It can quite often, knowledge-guided machine learning methods can generalize better outside of the training data or task, and they can ensure that the machine learning output is physically meaningful. Furthermore, methods for extracting knowledge from machine learning can increase transparency of machine learning models. And you might also gain into new scientific insights, which might come in the way of causal connections, spatial patterns and important precursors, or PDE representations. So if you combine all this together, you get some potential advantages that are pretty important. Number one, you might increase performance reliability of your machine learning models. Number two, you might increase trust in machine learning methods by weather and climate scientists who have to make these life and death decisions. And number three, you might get new scientific insights. Next slide, please. All right, so we're looking here at some sample methods for adding knowledge to machine learning. And this is what we call the forward direction, because you're adding scientific knowledge to the machine learning problem. Some sample methods include incorporating physical constraints into machine learning methods and other ways to help the system generalize outside of the training range. And you will see Tom Buechler talking about this in presentation number 4 today. Another method is to use transfer learning or meta-learning, which allows knowledge gained in one domain to be transferred to another domain. And you will see Sherry Wang touching on this topic. And in fact, you can look at the last one as being something that goes in both directions, because you're extracting knowledge and you're also adding it somewhere else. Next slide, please. So in the reverse direction, you use your machine learning to extract knowledge, scientific knowledge, from the data. And some sample methods include using explainable AI, for example, neural network visualization tools, to explore knowledge identified by the machine learning model. And you will see both Kirsten and Maria Molina talking about those topics. Secondly, there's using causal discovery to extract causal relationships, and you will see Marlene Kretschmer talking about causal inference and causal discovery. And another example is using machine learning methods to learn a system's partial differential equations from data. And you saw Laura Zanner giving a great talk about this in the opening session. So these are just some examples. Of course, there are more, but this gives like a good overview of some primary methods and how they're relating to the presentations you will see today. So I'm hoping this will give you kind of a big picture overview of what you will see. Next slide, please.
Okay, so Imme and I hope to introduce this session, and we thought it might be fun to tell a little bit about some of the work that we are doing here at Colorado State University as a way of introducing, again, these topics of KGML that you're going to hear about the rest of this afternoon. So two key methods that are used by our groups are causal discovery and explainable AI. And in terms of the causal discovery, which again, Marlene will talk quite a bit more about in the coming session, Imme's actually been, working in the field of causal discovery and climate research for almost a decade now, and we, as two groups, have really come together to do some work recently, thinking about subseasonal to seasonal prediction in this sphere of causal connections, thinking about how tropical storms, for example, may influence mid-latitude storms or the stratospheric polar vortex in the coming days to weeks. And I'm not going to talk too much about this here, other than these types of causal networks and trying to extract these relationships or teleconnections from one point on the globe to another is something we'll be hearing more about in the later session or in the later talk. And the second, as I said, the second key method used by our groups is really explainable AI. And this is where we have quite a bit of activity going on right now. So we thought it would be fun to give you a bit of a flavor for what type of work we mean by explainable AI. It has a really cool acronym with an XAI, but what does that really mean, right? So here we're just going to focus on our work on neural network visualization. Specifically, our favorite method right now is called layer-wise relevance propagation. And while we did not come up with or invent this tool, we are finding incredibly helpful for doing weather and climate science with machine learning, specifically with neural networks. So just big picture to introduce this method. Let's start with an artificial neural network. We've already heard about convolutional neural network and LSTMs. Just at its basic form, though, a neural network really is data going in to this network of connections between different values. So it's really, in essence, a feed-forward network is like regression, and it outputs a prediction. Now, the complexity and nonlinearities inside of this network allow it to learn many different pathways of predictable behavior. And we've already seen wonderful examples of how that can lead to better predictions. But a big question as scientists is, how did the network make its prediction? What did it learn? How did it do such a good job? And as scientists, we're often wondering why. We don't want to just make a prediction. We then want to understand why we were able to make a prediction. And so what can we expect from neural network visualization? I love this example that Imme came up with here. So just like a black backpack going through an X-ray scanner, at first when you look at the black backpack, you can't see anything that's inside. Same with this idea of a black box neural network. Now, when you put the backpack through the X-ray scanner, what you get out is not a perfect view of the contents of the backpack, but it's certainly better than what you started with. And that's how we think a lot about our neural network visualization techniques. They're not going to give us everything that's going on inside, but they're going to give us an inside view that's certainly better than the black box. And then, of course, the question is, how can we use this for science? So layer-wise relevance propagation is the tool that our groups are really using a lot these days. And here's the basic overarching concept. Let's say you have a classification problem where you input an image and you want to know the probability that, is there a cat in my image? So in this example, we have one specific image of our cat, and we've already trained our network. So now we're going to put this image through our trained network and output the probability that there's a cat in this image. Now, what layer-wise relevance propagation does is it takes that probability and it propagates it back through the network such that the output is a heat map, which you can see here with the red dots on the left-hand side. So here it is shown again. And what this heat map tells you, it's the relevant regions of the input for the network's prediction. So the idea is when the network made its prediction of the probability of that it was a cat, these are the regions that the network placed most of its focus. So here's a fun example use of LRP that came out of the group who invented this technique. So here's our task. Everybody, here's your task. I want you to decide whether there is a horse in each of these images. Okay, so a network was tasked, the CNN was tasked with this very job, and it got them all right. It figured out that there was a horse in each one of these 3 images. And as humans, hopefully you've all also agreed there's a horse in each of these images. But now we can use LRP to ask, how did the network figure out there was a horse? I know how I knew there was a horse, but how did the network figure this out? So what we can do is push each of these images through and propagate their relevance back to create a heat map. And here's the heat map output by LRP, where the red regions are the regions that were most relevant for the network's prediction that there was a horse. Now, you might be surprised because the reddest or brightest, warmest regions are not where the horse is, but they're in the bottom left-hand corner of every image. And if you look closely, you'll realize that is where the copyright symbol is for this particular set of images. That is, the network has learned that when it sees this copyright symbol, it's probably a horse. Okay, and in most applications, this is not what you want to happen, right? We want it to learn for the right reasons. And in this case, I think, at least I would say, this is learning for the wrong reasons here. So now we're going to go through 2 examples of how we are using this method to do science in weather and climate.
All right. So you've seen horses, you've seen cats. So the next question is, how can we use LRP in weather and climate? So here's a weather example, and next comes a climate example from Libby. So this is some of the work we've been doing where we've been trying to generate synthetic radar images from satellite imagery. Why would we want to do that? Well, satellite imagery is widely available, for example, in all of the continental United States, but radar is not. So it would be very nifty if we could just feed into a neural network our satellite imagery, and then out comes an estimate of radar imagery, specifically MIMS. So we're feeding in here 4 different channels of the GOES satellite system, channel 7, 9, 13, and Lightning. We feed in our neural network, and out comes an estimate of radar imagery. And so we trained our neural network, and it was performing reasonably well. But then, of course, the question was, how does it do it? How does it come up with this estimate? So next slide, please. So of course, we used our favorite method, LRP, for this purpose. So again, the question was, our neural network performs well, but how does it do it? What kind of strategies does it use to come up with pixel values of radar, also known as MIMS? So what LRP can tell us is where in the input is the neural network focusing when estimating large values of MIMS at the output. And we used LRP, and I won't go into the details. I have the paper here on top. If you just Google Ebert-Uphoff and Hilburn 2020 archive, you will find our paper, which is also about to appear in BAMS. But the key point is that we used LRP to find 3 different strategies by just looking where the neural network was looking. And we found that the MIMS is estimated near 0 unless one of the following 3 things happening. Either there's presence of lightning, or there's presence of cloud boundaries, or there's presence of cold cloud tops, which all makes meteorological sense. So now we have a qualitative understanding of how a neural network is thinking, and we can explain it to a meteorologist. We can say, well, the neural network is going to estimate something close to 0 unless it sees lightning in the GLM's channel, or it sees cloud boundaries or very cold cloud tops in the ABI channels. So again, we gain qualitative understanding, and that increases trust in the method. Next slide, please.
So in Imme's example, she showed how we can use LRP to gain trust in our method. For example, the horses, we would not have trust, but in her example, we see, okay, maybe this method is actually predicting this radar image for the right reasons. In this example, I want to explain how we're using LRP to discover new science about the climate system, specifically thinking about climate change in the 21st century. It's really a signal to noise problem. So if you look here at this plot, this is a mean predicted change in temperatures between the beginning, or between 1920 and 1939 and the end of the 21st century, so 2070 to 2099. This has been averaged over many climate models, 29 different climate models. So we get a very smooth, pretty picture. And as you can see, first of all, most everything's red, or everything is red, and this is global warming, the Earth warming up with anthropogenic emissions. And we see that some regions are warming up faster than others. But what's hidden in this pretty mean average picture are two sources of uncertainty. The first is structural model uncertainty or model disagreement, and the fact that we have many different climate models that all simulate the physics of the climate system differently. That's all been hidden because I've averaged over all of these models. And the second is the concept of internal variability or climate noise. The fact that on any given day, on any given year, the climate system has a certain amount of noise associated with it that we will never be able to predict. And again, that's all hidden in this one average plot. Now, this is nice and we can make this plot, but the issue is the real world is not an average of 29 different climate models. It's really just one of these. So when we look at something like observed present day trends in temperature, how can we tell which changes are the signal in this picture and which trends that we see or changes are the noise in our single one observed Earth? So we got together and thought about this and came up with sort of a funny setup that's turned out to be really helpful in thinking about climate change patterns. So specifically what we did is we set up our network to train something incredibly boring. We are training our network to predict the year of a map. So everybody in your head, think about the year you were born. Somebody could have made a global temperature map of that year. What I want to do is I want you to be able to feed that map into a neural network, and I want it to predict. In this case, we're doing fuzzy classification, but you could think of it as a regression problem as well. I want to predict the decade, if you will, that map came from. Okay, now, right now for this example that I'm going to show, we're going to train and test on climate model output. So we do have data everywhere for every year. So if you stop and think about this for a while, and it really took me a while to think about it, you figure out that the network has to learn regional signals that are reliable indicators of the year in order to do this problem well, in order to predict the year correctly. And this is hard because of all the noise in the climate system. It needs to learn the patterns of forced change in order to predict the year correctly from a single map. So we trained our network and it turned out it did okay. So that's shown here where the actual year of the map that we fed the network is on the x-axis and the predicted year is on the y. So a perfect guess is going to be along that one-to-one line. You might notice the different colors. Well, the gray dots, which are hard to see, were our training simulations, and the colored dots were the climate models that were only used for testing and validation. So a few cool things that we saw is, first of all, the neural network doesn't do a very good job for the first few decades of our simulations up until about 1960. And that's because the climate change signal is so weak that it's unable to figure out what year it is because of all of the noise. But then around 1960 or so, the network finds regional patterns that tell it what year it is, and it's able to do a relatively reasonable job in predicting the year from then on into the 21st century. And you can see it does a better and better job as we go further and further into the 21st century because the climate change signal becomes stronger and stronger in comparison to the noise. Now, I will mention that climate models are wonderful tools, but they have issues. And so it's possible that our neural network could learn wonderful things from climate models that have absolutely nothing to do with the real world. So as a test, once we've trained our model, our neural network, we then take maps from the observed Earth, the real world we live in today, and we push those through the network and we say, guess what year it is? And those guesses are shown in the white dots here. And what you can see is it gets the year generally correct. Now that's very exciting in my view, because what that tells us is what the neural network has learned from these climate model simulations is applicable to the real world. Okay, so I've just made a big deal about predicting the year, and you should not be terribly impressed because we all know what year it is, and we all knew what year it was. So what have we really done here? Well, this is not the exciting part. The exciting part is now using layer-wise relevance propagation to figure out what the neural network learned in order to predict the year in the first place. That is, we have our network set up on the top here, but we can now propagate backwards through the network using LRP and ask which regions are relevant for correctly predicting a specific year. So for example, we've done this, and for the year 2015, these are the relevant regions shown as the dark red colors for predicting the year from a map of surface temperature. And I mean, I could talk a lot about what all these different patterns mean. We see the Southern Ocean jumping out, for example, regions over Asia and the North Atlantic. But these start to tell us where those forced components or where temperature is responding in a way that makes it relevant to know the year. Now we can do this for more than just 2015. We can do this for lots of different decades. For example, I'm showing 1995 through 2095 here. And what we can see is because the network is nonlinear, it's able to pick up time-changing patterns of forced change. That is, the 1995 picture does not look like the 2095 picture. But you also see some very interesting signals. For example, we believe that this relevant region over Southeast Asia in 2015 may be related to aerosols being output because they peak during those decades. You'll also see that the Arctic does not play a substantial role in telling us what year it is, because although the Arctic warms substantially with climate change, it's also very noisy, and climate models tend to disagree on the actual response. And so the neural network has learned to ignore the Arctic and look elsewhere when determining what year it is. So those are just two ways that we've been using explainable AI to think about science and do new science, as well as have faith in what our networks are actually learning and making sure they make physical sense. But those are just some examples of how KGML is being used in our groups and in weather and climate. And now what you're really here for is to listen to our upcoming speakers. So we have a great set of 5, really rising leaders in this field of KGML for weather and climate, who are going to talk about a variety of ways, both the forward and the backward direction, in adding and extracting knowledge from these tools. And finally, just as a reminder, you can find all of this on our website, but I will just note that our break is from 2:40 to 3 o'clock rather than 2:50 as it says on the website. And Imme, anything to add before we move on?
One thing I think we should add is that we didn't properly acknowledge our NSF sponsorship. So if you wouldn't mind going back to slide number 1, all the way, if you could. I just wanted to acknowledge NSF sponsorship for this. And as you know, this is all part of a bigger project that we have at the University of Minnesota with the other universities that I mentioned here on top. So I don't want to neglect that. Thank you. And with that, should we move on to the first presentation? We're actually 5 minutes ahead of schedule. I think there's some questions. So maybe we take some questions since we have 5 minutes.
That's just fine.
Okay. So there's one question here that says, regarding guess what year it is, if you train it using paleo data, assuming you had such, would it break the neural network?
Well, if we trained it with paleo data, I'm not sure how it would break it. If we actually had that data, I think it would just, it could help. Well, because paleo climate does have very large cycles that are being forced externally from, say, the solar cycle, and larger forcings than just the climate noise, I think it could actually learn something. One thing we have done is we have tried to train it with a climate model simulation that has no forcing in it whatsoever. So in essence, it should fail because there is nothing to learn about the year. And indeed, as expected, it fails miserably.
All right. Another question, have you compared your result on slide 29 to a simple sorting based on global annual mean temperature?
Yes. So for those of you familiar, you might say, well, hold on a second. We know every year the climate gets warmer, so the neural network could just be taking the mean temperature over the globe to help it predict the year. So in first answer, our network does better than just the global mean temperature. But more importantly, I didn't show these results, but a big part of our paper is taking the global mean signal out. So every year's map has a mean of 0. So in that way, we force the network to only learn the regional patterns and relationships in response to climate change. And what surprised me is it does quite well, almost as well as what you just saw, suggesting that it is not only relying on the global mean temperature to make its prediction.
Okay, I think we have time for one more question. Layer-wise relevance propagation looks like a great tool. Any thoughts on how it could be used to look into processes?
Imme, would you like, I've done a lot of talking. Would you like to answer?
I think
can
it's
also
a better
answer.
one to answer that question there. I think that's for you.
Yeah, so, okay, so in terms of processes, I think we could sit and brainstorm quite a few. I believe our next speaker, Kirsten, is going to start talking about specific processes that we expect as scientists relate one region of the globe to predictions in another. And she will be using LRP to make these predictions or to understand these predictions. So I think in that sense, our next speaker is going to be a great example of how we can use this to understand processes. It can also be helpful if you have a network where you've input lots of things you think might be important in terms of processes and mechanisms, and you output a prediction and it gets it right. You can use LRP to go back through the network and ask which of those inputs were most helpful. For example, was it soil moisture or was it surface temperature or precip that helped me predict this future state of the atmosphere or Earth's surface. So, but I think our next speaker is going to be a great example of that.
So with that, I would say we can look at some of the remaining questions in the panel session at the end, and it sounds like a perfect transition to Kirsten's talk. Take it away, Kirsten.
All right, thank you. My name is Kirsten Mayer. I'm a PhD student at the Department of Atmospheric Science at CSU. I'm going to be talking about utilizing interpretable neural networks for subseasonal prediction. While I'm applying it to subseasonal prediction, we can really apply all these tools that we're using here for any type of prediction problem. I'd also like to mention my advisor who's been working on this with me and also my funding from the NSF. So first I'm going to talk about what subseasonal means. Subseasonal timescales are these 2 to 5 week timescales. So subseasonal prediction is prediction on these 2 to 5 weeks. So here I have a schematic of prediction scale on the y-axis and time on the x-axis, where I have hour, day, and weeks marked. So as you can see, when we're at weather timescales, so these hour-day predictions, we can see these really high prediction scales. But as we approach a week, we can see this stark decrease in prediction scale. And this is due to minor errors in initial conditions of our models that can lead to chaotic growth over time. You can think about this as the butterfly effect. You've all experienced the fact that we don't have very good prediction scale on those time scales. For example, if you were planning a picnic, you would probably trust the weather forecast an hour out or to a day out and whether it's going to rain. But on these 2 to 5 week time scales, let's say you're planning a picnic for a month out, I doubt many of you would use the actual prediction for where you should have your picnic. So in order to predict on these 2 to 5 week timescales or these subseasonal timescales, we look towards forecasts of opportunity where certain conditions can lead to more predictable behaviors than others. So beyond these weather timescales, these days and hours, we must look for specific states of the Earth system or these opportunities that lead to enhanced predictable behavior. One of these opportunities is known as the Madden-Julian oscillation for subseasonal prediction. The Madden-Julian oscillation is a dipole of suppressed convection or precipitation and another of enhanced precipitation, where the teal indicates regions of enhanced precipitation, or you can think of a really cloudy region, and the tan indicates a really sunny region compared to normal. So when the MJO is active, we can use information about where it's located and how strong it is to predict what will happen over the Northern Hemisphere, such as North America and the Atlantic. But the MJO isn't always active, and this is where the idea of opportunities comes in. Sometimes when the MJO isn't active, you can think of the tropics as a bunch of small ripples or a bunch of storms that are occurring. And this is a pretty chaotic system, and it makes it very difficult for us to predict how the ripples will end up affecting us over the northern hemisphere. But when the MJO is active, you can think of it as one large ripple, where this ripple propagates into the northern hemisphere and can start impacting our weather. And there's been studies to show that the MJO leads to consistent and coherent weather patterns over the United States. So when the MJO is active, we can use the information about the state of the MJO to predict what will happen to weather in the United States and North Atlantic and Europe. So where do neural networks come in? How can we use neural networks for subseasonal predictions? So the question we're trying to ask is, how can we utilize neural networks to identify forecasts of opportunity for subseasonal prediction? So in order to do this, we need to answer two questions. So can neural networks identify the forecast of opportunity for subseasonal prediction? Well, they'll need to be able to identify when. When do we see periods of enhanced predictability, or when are these opportunities? And the second is why. Why is there predictability, and where is it coming from? So in order to orient us, I've made the neural network setup on this slide for the subseasonal prediction, where we input tropical storminess. So again, where this teal color indicates enhanced rain, and this tan color indicates suppressed rain or very sunny weather. And we input all days. So we input days where the MJO is not active and days where the MJO is active. And we want to see if it can pick out these opportunities. We input individual days into our hidden layer to train it. And we just use one layer, and it's a very simple network. And we're trying to get this network to predict the circulation over the North Atlantic 3 weeks later, the sign of the circulation. You may be wondering why we're looking at the North Atlantic, since it's over the ocean and no one lives there. Well, this is because this is a region where storms are generated and steered into Europe and are very important for forecasting European weather. So the first question we're going to try to figure out how to answer with a neural network is when. When do we see these periods of enhanced predictability? Well, we use an idea called model confidence, where we use the softmax activation function to convert our output from the neural network into something like a probability, which we call confidence. So the neural network outputs some numbers, some random numbers. And let's say we have a 3 and a 1. So the neural network is predicting the sign of the circulation over the North Atlantic is going to be positive. Now we can run that through the softmax activation function, and it'll pop out a probability, or what we refer to as a confidence, where the model is 88% confident that its correction is correct. So how can we use model confidence as a forecast of opportunity? Well, if we start looking at neural network confidence thresholds, we can compare the accuracies at different levels. So for example, when the neural network confidence threshold is low, we can see that we have an accuracy around 60%. But as we increase this neural network confidence threshold, so as the model becomes more and more confident in its predictions, you can see the stark increase up to about 72% accuracy. So as this confidence threshold increases, our accuracy increases, which suggests the model is finding these forecasts of opportunity. And we would expect this since we know as domain scientists that the MJO is a thing for subseasonal prediction. And so while the number of predictions go down, while we increase our neural network confidence, we found these opportunities to have higher prediction skill. So in order to make sure that this wasn't just a fluke on one model, we actually trained this model 100 different times with random initialized weights. And we wanted to see how the accuracy changed when we look at no confidence whatsoever, and when we actually look at the 10% most confident predictions. So when we're ignoring confidence and we just look at all the predictions, you can see that the accuracy is around 57%. But when we look at the 10% most confident predictions from each model, we can see a stark increase in the model accuracy up to about 67% for all these 100 models. So to go back to the question, when do we see periods of enhanced predictability and how can neural networks pick this out? We can really look at model confidence in order to determine these forecasts of opportunity. So next I'm going to talk about why. Why is there predictability? Because this is really the science question. This is what we're trying to get at. Where is this predictability coming from and how can we use this for forecasts in the future? So of course we use layer-wise relevance propagation, which is our favorite tool, or LRP, and we're basically asking, what did the model learn? So in this case, we're asking, what are the relevant physical structures of storminess, or the storms in the tropics, that lead to enhanced prediction skill over the North Atlantic 3 weeks later. So I'm just going to briefly talk about what layer-wise relevance propagation is again. This example was just given, but let's say we have a neural network that's trying to decide whether an image is a cat or a dog. Well, you input the image into a trained neural network and it pops out a prediction of whether it thinks it's a cat or a dog. Let's say it was a correct prediction of a cat, and we can tell that this is a cat. So we can go back through our trained neural network, uncover what's inside the black box, and trace back and create a heat map of what the neural network actually looked at to determine that this picture was a cat. And so you can see that it's picked out some ears, maybe the nose, some eyes, etc. So you can also do this for other things like a hammerhead shark, of course. And you can see that for the hammerhead shark, it's picked out the hammerhead shape and fins in order to determine this. But you can also do this for objects. You don't have to do this on animals per se. So here's an example of a coffee cup, and the neural network determined it was a coffee cup because of the rim mainly, but then also, if you can see this, it has the handle outlined and the base of the coffee cup. And the most common example that's used for LRP is handwritten numbers, where the neural network can pick out what regions were important to identify that these were the certain numbers. So how do we apply layer-wise relevance propagation to S2S prediction? So we input tropical storminess into a hidden layer and try to guess the sign of the circulation 3 weeks later. So when we're using layer-wise relevance propagation, we want to take these correct predictions of the sign of the circulation over the North Atlantic and ask what the tropics was doing 3 weeks earlier. So what are these relevant physical structures of storminess in the tropics, or what do the tropics look like for accurate predictions over the North Atlantic? So now we're looking at heat maps of the storminess over the tropics that was important for these predictions over the North Atlantic. And as you can see, we have these two hotspots of heat maps. Hotspots where we have one over the maritime continent and one over the Western Pacific. And if you actually composite on these days, you can see that this is a region of enhanced sun where it's very dry, and this is a region of enhanced precipitation. And so it's actually picking out what's something that looks like MJO phase 7 and 8, which we know can impact our prediction skill over the North Atlantic. But we can also do this for different timescales. Let's say we want to predict 2 weeks out instead of 3 weeks out. So what did the tropics look 2 weeks before we made our prediction over the North Atlantic? Well, again, you can see these two hotspots, one over the maritime continent and one over the Western Pacific. But we also see these features that are not typically MJO-like, like this hotspot that propagates into the Northern Hemisphere a little further. And then we also have these hotspots over Northern India and Pakistan and in the Middle East. So in order to understand these more, we use clustering. And what's super nice about LRP is that you can have individual LRP maps for each prediction. So for each prediction that is correct, you can actually figure out what the model looked at for that specific prediction to determine that this was the correct sign. So we use clustering, which is, we use k-means clustering, and we decided to group into 2 groups to see what the neural network is picking out. And when we do this, our first group is really showing this dipole, these two regions of hotspots, one over the maritime continent and one over the Western Pacific. And we can see when we look at the actual storminess during these times that there is enhanced precipitation over the maritime continent and it's sunny over the Western Pacific. And this may be associated with MJO phase 2 and 3. So it's picking out this MJO signal. But what's really interesting is in the second group, it's picked out these not MJO-like signals. And so these may be new forecasts of opportunity that we've never seen before that's provided by looking at LRP. So we also did this for week 3, but as you can see that these are very similar. We have the two hotspots, one over the maritime continent and one over the Western Pacific for both of these. So clustering can be a useful tool for identifying one or more forecasts of opportunity and some that we may not even know. So how we answered the question, why is there predictability? Where is it coming from? We can use layer-wise relevance propagation to do this, to look for these forecasts of opportunity. So we can use neural networks to further understand subseasonal prediction. But like I said at the beginning, this isn't just for subseasonal timescales or for atmospheric science. If you're doing any type of prediction that uses forecasts of opportunities, this could be a great tool where model confidence can identify these opportunities for increased accuracy, and layer-wise relevance propagation can open this black box that we consider a neural network. So we can learn how the network has made its prediction. And this allows us to do the science that we're interested in. We can find new sources of predictability from extracting knowledge from the actual neural network. If you're curious and want to know more about this, you can look at these papers. Otherwise, you can send me an email. I'm also on Twitter.
Hey, Kirsten. So in terms of questions before we move on, one question is, can you think of possible ways to measure uncertainty of your heat maps?
Totally. So there's actually a new method from the LRP group, and I haven't looked into it yet, but that's one of our next steps in terms of measuring the uncertainty of our heat maps.
Great, thank you. I guess with that, we can move on. And again, we will be taking questions for the whole panel. We can talk about LRP and all the other cool tools we're going to hear about next at the end of this session. Hey, Marlene, you're muted. Can you unmute yourself?
Okay, sorry for this. So hi, my name is Marlene Kretschmer. I'm a postdoc at the University of Reading, and I will talk about causal inference and causal discovery in the context of teleconnections. And first, I'd like to acknowledge my co-authors, Ted Shepard, Elena Sajjodo from Reading, Giuseppe Zappa now in Bologna, as well as Alberto Arribas, Rachel Prudden, and Robinson and Adams, all from the Math Office Informatics Lab. So what motivates this work is that an improved understanding, as we have also seen in the previous talk, of teleconnections is key to reduce uncertainties about regional weather and climate predictions. And so typical questions posed in this context are, for example, how much does ENSO contribute to temperature variability in region A, or which processes drive precipitation in region B? So the task or the challenge I'm addressing here is kind of extracting this causal information from data. Machine learning, and in particular deep learning, are of course extremely powerful to classify spatial temporal patterns, but they are not necessarily designed to improve process understanding or kind of to answer these causal questions. So at least in the context of teleconnections, I here also argue for an approach which is embedded in the mathematical concept of causality. And so in the first part of my talk, I will talk about causal inferences and how we can use it to quantify cause effects from data. And then in the second part, I will talk about causal discovery, which is more on this intersection with machine learning, and we'll kind of briefly discuss how this can be used to learn causal structures from data. Okay, so causal inferences is what one could also call knowledge-guided statistic. And so very simply speaking, it sets the rules of when we can actually quantify cause effects from data. What is required and what is actually the first step of any causal inference analysis is using our knowledge to set a plausible causal model. And this is usually shown in the form of a network. So again, here you can think of these nodes ABC as processes describing something like ENSO or precipitation, etc. And so this network encodes all our domain knowledge and our assumptions of the underlying processes which generated the data. And explicitly outlining these assumptions first has then the advantage that we can draw some logical implications from this model and test if they're supported by the data. In this example, D and B, we would expect them to be correlated or to be statistically associated because they're both driven by process A. But once we control for A, we would expect them to be independent. If they're not, then our assumptions must be wrong. And then further, we can use causal inference rules or kind of these graph rules to estimate the causal effects. And it's always based on this model, and it's basically about blocking the influence of other nodes which might affect the link we are interested in estimating in. So for example, if we want to estimate the causal effect from A to B, we do need to control for this common driver effect C. To give some intuition of how we can combine scientific theory with data analysis, I prepared some very simple real data examples. So in this case, I have data of precipitation in Denmark and the Mediterranean in summer. And the data here is NSAP reanalysis data. And all time series have been standardized. There's actually quite a strong statistical association between them. And for example, if we would assume some linear dependence and we would regress Denmark precipitation on Mediterranean precipitation, we would find a significant regression coefficient of minus 0.25. But, well, of course, as climate scientists, we wouldn't interpret this causally because we know from different lines of evidence that both regions or precipitation, both regions is driven or is affected by the position of the North Atlantic storm tracks. For example, calculated or expressed by the North Atlantic Oscillation Index. And so we can test this, or we can test our knowledge with the data. And in the linear case, kind of controlling for the common driver, in this case NAO, actually just means including it in our regression model. And you see, if we include the NAO, then actually this regression coefficient drops to 0. So the kind of data generating model we had intuitively in mind can fully explain the statistical association we saw between Denmark precipitation and the Mediterranean. And this strong correlation really just comes from this causal effect the NAO has on both regions. This is another example, but one in which controlling for a different process is actually harmful. So this network summarizes a large body of literature of how ENSO affects precipitation in California in winter via the jet stream. So if we wanted to estimate the effect of ENSO on California precipitation, and if we would put both ENSO and the jet in our regression model, so this is, I think, something we actually do in climate science, just putting everything in, then we would actually get a regression coefficient for ENSO, which is 0. This, of course, makes no sense, but what happened here is that since the causal effect of ENSO is completely mediated via jet or via the jet stream, we basically regressed out the effect we wanted to measure. So the correct way, again, assuming this model, assuming we agree on this model, would be just to regress California precipitation on ENSO directly without controlling for anything here. We could also kind of estimate these two links separately and first estimate the effect of ENSO on the jet and then of jet on California precipitation. And then the product along this, this path is actually the same as estimating the impact of ENSO directly. This is a third example. Again, it includes ENSO and its effect on the jet stream, but this time on the southern hemisphere. And we have this direct pathway from ENSO to the jet, but there's also an influence of ENSO on the polar vortex in the stratosphere. So, and which then again affects the jet stream. So we kind of have ENSO affecting the jet via the so-called tropospheric pathway and then via the stratospheric pathway. If we're interested in the total effect, again, this could be done quite easily because there are like no confounding factors in this model. And we would estimate this effect of 0.18. But if we wanted to, if we were interested in kind of the contribution from the different pathways, we could also calculate this. And so for the tropospheric pathway, we do have to block this flow of information via the vortex. So we have to include the vortex in our model, in our regression model. And then we see that the effect of ENSO drops to only 0.05. And then for the stratospheric pathway, we could first quite easily estimate the effect of ENSO on the vortex. There again, there are no confounding factors here. But when estimating the effect of the vortex on the jet, we do have to control for the effect of ENSO, which is a common driver in this case. And then the stratospheric pathway is again this product of these two links. And if we would sum up the stratospheric pathway with the tropospheric pathway, then you see that it exactly adds up to the total effect. So these previous examples were quite simple and also show processes with already well understood. But of course, the situation can be more complicated. As for example, in this case, this is from a paper which is currently under discussion at Weather and Climate Dynamics. And in this paper, we try to address the role of Arctic sea ice loss, or in the Sakura sea region, and what this plays for future polar vortex changes. And this is actually quite a controversial topic. So what we did here is, as a first step, really to kind of try to summarize all the previous work on this topic, and kind of included all these findings in kind of a plausible model of the involved processes. Here shown in the form again of a network. And you can see, well, things are a bit messy now, and I won't go into detail, but you can see there are several mechanisms involved or likely involved. And also we see the self loops, which in this case represent strong autocorrelation on the subseasonal timescale. But again, based on this model and making a few choices on the data and timescales, we could then actually, or we tried to estimate this causal effect, but again, by controlling on the potential confounding factors. And we do this here for the different CM5 models. And the key point here is that by setting or by outlining our assumptions first, we can have a more reliable and a more plausible estimate of the causal effect. Okay, so in the second part, I will now briefly talk about causal discovery. Because I guess, well, typical criticism of causal inference is that that's very nice, but of course we need this causal model. But what if we don't have this model? And this is, this task is sometimes called causal discovery. So what we have here as kind of input data is time series, again, of different processes representing different time series representing different processes we're interested in. And what we want is to find or to learn the causal structure of these different processes. There are some things called causal discovery algorithms to achieve this. And Libby also mentioned this. Also, that group did quite a lot of work on this. I've been involved in something called this, the PCMCI algorithm. There are a few bit more assumptions in it, but the basic idea is that you can test if process A influences B or there's a causal effect by iterating through different combinations of conditions from your input data in kind of an optimized way. In this way, you could, or you try to filter out all the non-causal spurious correlations you find and come up with this causal structure. It has this, or this PCMCI algorithm has been particularly designed for climate data and kind of can deal with typical things like strong autocorrection, for example. Also, there have been recent advancements of this algorithm. For example, with Elena Sadoro, we have a paper recently under review where we combined this algorithm with a mark switching algorithm and to make it also capable to deal with non-stationary causal effects, for example, in the presence of some kind of persistent background regime. And also it can now deal with instantaneous links and much more. And I suggest to follow the work by Jakob Runge on this topic. But we can also go a step further and pose and address the situation when we don't even have time series. But all we have is our gridded climate data from observations or climate models, for example. So we want, from the gridded climate data, we want to extract time series, which we then put in our causal discovery algorithm. And this is, of course, pretty much an optimal situation for machine learning, kind of to find these spatial temporal patterns to get from gridded data to time series. And for the case when we not interested in the full causal structure, but more like finding some causal drivers of some process C, we, in this 2018 paper, we propose one very basic cluster approach of how we can first find these strongly correlated, likely relevant regions, and then extract the causal drivers of these. We have some recent papers where we apply these tools, for example, on the Indian summer monsoon, or to predict Atlantic hurricane activity or crop yield. And I don't have time to talk about these in detail, but the key point here is that even it is a machine learning approach, so we start from gridded climate data and want to predict some target variable. They all need a lot of domain knowledge, and I think in the climate case, I think especially the time scale is really difficult to address or challenging to address because it's a fully coupled system and several different relevant timescales. So yeah, again, I think it's impossible without the domain knowledge. So this is my my conclusion slide. So the point I try to make is that I think that in climate science, the physical concept of causal effect is very natural to us, but yet we don't really capitalize on the mathematical formalism of this concept. But I think like including our causal knowledge and all the knowledge we have already on the system is really essential it's essential to include this in our data analysis to also answer these causal questions which we pose. I also think that kind of combined with causal discovery algorithms, we can also, or these tools can also help to close knowledge gaps. For example, when it's about the different direction of causal interaction, which we are not aware of, maybe. And then finally, I think that especially at this intersection with deep learning, which is, I think, which is of course some ongoing research activities, but I think the overlap is not large enough yet. So I really think that combining these ideas and tools with deep learning, but also expanded AI is extremely promising. And I wanted to kind of end with a very optimistic statement. So I think it's really an exciting time to do causal guided machine learning, as there's really like a lot left to do both from the application and the lab side. So thank you.
Thank you very much. Great presentations. So we have a lot of questions actually right now on Slido, and we still have 8 minutes left before the break, so I thought maybe we can take a few questions here for Marlene. One question is, Marlene, can you identify a hidden connection due to an unknown factor if you draw a map like this and include one or more unknowns?
So it's definitely possible also to kind of explicitly include unobservables in your network and in your assumptions. I'm not sure if you the person asking the question referred to the causal discovery part or the causal inference part, but I think for both it's possible, but again, depending on assumptions on the data.
Thank you. Another question. Can you identify a hidden connection due to an unknown factor if you, no, sorry. In experimental ecology, we would sometimes manipulate a system to identify a causal relationship. Is there an analog in your causal work?
I think it's exactly what's meant by a causal effect. It's not the association between X and Y, which we can perfectly measure, but it's like, what if we intervene in the system? And the causal inference is about kind of predicting this in intervention, but only based on the available data of the observed data we have. And again, like mathematically, this is possible or shown to be possible if you have a causal model. So this is the main assumption. And of course, let's say in science, it's a bit more tricky than that because we have usually some more complex systems. And again, like I said, in climate, we have different timescales, etc. But yes, so mathematically, it's possible if you have a causal model.
Okay. Are examples 1, 2, and 3 based on multivariate time series? If so, did you treat them as IID in order to get this thought relationship?
Sorry, I didn't understand the first part of the question.
So the question is, in your examples, number 1, 2, and 3, these are multivariate time series, right? And if so, do you treat them as IID?
Yeah, well, in this case, we used seasonal mean data to exactly not think about at least of autocorrelation, but I guess it's true. One could question the causal model and say, well, what about more kind of, I don't know, decadal variability, etc. But I think this is again the deal. Like we make the assumptions explicit, and then we can discuss or we can interpret results based on these assumptions. But it's also completely fine to kind of challenge the assumptions and make better ones.
Okay, one more question for Marlene and Kirsten, if it's okay with you. Here's one more question that I think you could answer, but I first asked this question here to Marlene. How do you account for possible false discoveries, given that there's so many possibilities?
So in the causal discovery part, there are different ways. I guess the basic idea is that you have some kind of significance thresholds or significance levels there, and then you can have, well, you have multiple testing involved, but you can then also apply false discovery rate corrections on your tests. And this way, we actually we showed this in the Science Advances paper that you can then control your false discovery rate to the before set significance level of, I don't know, 5% or so. And this is of course especially relevant in a high dimensional setup.
Great, thank you. So we'll take more questions for you also in the panel session at the end. So here's a question, Kirsten, that relates to LRP that I was hoping that maybe you would be willing to answer. For LRP, does the spatial arrangement of hotspots in the heat map or the time series matter, as well as the actual values in aligning images to years? Oh, I think that's probably a question to Libby, though. Sorry.
But I think that can be rephrased as just, does the spatial arrangements of the hotspots as well as their values matter in the prediction? So does it matter, I guess, where your blobs in the tropics are? That's how I'm interpreting the question. Instead of predicting the years, in predicting the North Atlantic storms.
Yeah, the location of the blobs are really important, and we were specifically looking for the MJO, and we knew that there was spatial dependence in the tropics in terms of the structure. And so we also used lasso regression in order to account for this. But yeah, does that answer the question?
Yeah, I think so. And I think the important point is here that at least in your example, I believe, and at least in my example in terms of the years from the question, that the spatial arrangement is everything, because that's the process, that's the mechanism. It doesn't just matter if there's a blob somewhere. It really, to tie it back to the physics, it matters where that blob is, whether it's a specific process like the Madden-Julian oscillation, or in my examples, it could be the fact that the land heats faster than the ocean. So it's we actually see the network pick up on the difference in heating or warming between the land versus the ocean. And that's how we can bring it back to, again, to physics. So.
All right, here's
Great.
one more question. One more question that I thought I could throw out for Libby and Kirsten. Is it possible to have a measure of uncertainty on the red spots from the heat map being good predictors?
Yeah, so I mentioned that there's recent work on LRP uncertainty by the LRP group, but you can also just train a bunch of models and see what their LRP looks like. And we did that, and we found that they generally look the same in terms of what it was outputting. So that's how you can, one way you can look at uncertainty.
All right, thank you. I think with that, it's time to take an early break, 2 minutes early. We will meet again in 22 minutes at right on the hour. So thank you, everybody.